Chapter 1 of the Romance of Modern Engineering. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Read by Krista Zaleski. The Romance of Modern Engineering by Archibald Williams. Chapter 1. The Harnessing of Niagara. It is indeed hard to conceive that anyone in full possession of his senses could stand unmoved in the presence of a great waterfall. The sight of huge masses of water, tumbling as it were from the blue of the very heavens, dissolving into arrowy streams as they descend before the final crash into the mist-laden gulf below, must appeal even to the most brutalized mind by its sheer majesty and magnificence. What then are the thoughts of those whose emotions are strings easily attuned to the grander moods of nature? The first impression is doubtless one of awe, called forth by the involuntary comparison between our own insignificance and the immensity of the force before us. What right have we, frail creatures of the day, to speak of lordship of creation face to face with this watery avalanche that has thundered down for centuries, nay, thousands of years? What can human art avail against the violence of those ceaseless, seething torrents, stunning our ears with sound, dazzling our eyes to weariness by their motion? Then follow what we may call the secondary emotions. The poet feels the inspiration of descriptive verse, the artist reaches for his pencil, the engineer or man of science, not less alive, perhaps, to the artistic beauty of the scene, yet from habit and profession sees here a mighty source of power, of motive force to drive the myriad whirring wheels conjured into being by civilization and its needs. "I look forward," said Lord Kelvin at Niagara Falls, "to the time when the whole water from Lake Erie will find its way to the lower level of Lake Ontario through machinery, doing more good for the world than that great benefit which we now possess in the contemplation of the splendid scene now presented by the waterfalls of Niagara." On another occasion, another famous electrician, Sir William Siemens, looked upon the scene with similar thoughts. The stupendous rush of waters filled him with fear and admiration, as it does everyone who comes within sound of its mighty roar. But he saw in it something far beyond what was obvious to the multitude, for his scientific mind could not help viewing it as an inexpressible manifestation of mechanical energy. And he at once began to speculate whether it was absolutely necessary that the whole of this glorious magnitude of power should be wasted in dashing itself into the chasm below, whether it was not possible that at least some might be practically utilized for the benefit of mankind. Footnote from William Pohl's Life of Sir William Siemens. End footnote. It seems as if we may trace the finger of a perverse fate in the necessity that drives us, in an age when man is peculiarly appreciative of the beauties of nature, to invade with our instruments and machines some of the fairest spots on earth. To obtain a good water supply, we throw a huge mass of masonry across the Nile, and dam lovely valleys. To furnish us with timber, stately forests are leveled. To yield us coal and iron, smiling countrysides are disfigured by towering chimneys, and the atmosphere filled with a foul reek. And that our source of energy may be in proportion to our wants, the rushing mountain stream in Norway, Switzerland, Italy, France, and elsewhere is hemmed in by walls and weirs, and its only way to freedom lies through huge pipes to whirling turbines. Much as we must regret these things, we know that they are inevitable. Many of the conditions of life are changing. Today, that nation is ascendant which is not necessarily hardiest, or numbers the bravest hearts and stoutest arms, but, as we are told, the one which can produce the cheapest ton of steel. In other words, wealth holds the balances. Wealth depends on commerce. Commerce comes to those who are able to hold their own against the world in the fierce struggle of economical production. To carry the train a little further, economical production is based upon a plentiful supply of cheap energy, whether in the form of motive force or heat. The manufacturer is so eager to clip off a decimal of a cent here or a fraction of a penny there from the cost at which he can produce his goods that any method for cheapening the prime mover, power, of his factories is gladly welcomed. The engineer is always busy bringing the latest appliances of science to his aid. We hear of enormous steam engines, many times more efficient than those of half a century ago, of great machines actuated by explosions of gas, formidable competitors to giant steam, and water power in its newest developments is fast pushing its way to the front, threatening both steam and explosive vapor. Coal fields are exhaustible, oil fields are exhaustible, but a river flows on forever. Once in harness, water becomes man's servant for the ages. As a consequence of the new lease of life given to water power, we may expect to see great changes in the industrial world. Hitherto, trade and manufacture have gone to those countries which possess well-worked coal fields. In the future, a bid for supremacy will be made by those districts where the force of gravitation, as represented by falling water, may be cheaply transformed into other forms of energy. Numerous experiments and statistics prove that the steam engine has almost reached its limit of economy. We cannot expect to get much more power from every pound of coal we burn than we do now. The cost of raising that pound from the bowels of the earth tends to increase as the supply decreases. Many great water power installations are already in full working. On the Rhone, the Rhine, the Adda, the Reuss, the Aar, hundreds of thousands of horsepower are daily produced at the turbines, and flashed noiselessly to thousands of machines through great cables pulsating with electricity. But at Niagara, the electrical mecca of the world, nature has furnished mankind with the most magnificent of powerhouses. Here the overflow from 4 lakes, or rather inland seas, linked so as to form one huge reservoir of 90,000 square miles, is herded by cliffs into a narrow channel and compelled to make a magnificent leap of 165 sheer feet into the lower river. The figures are almost appalling. A solid wall of water 20 feet deep, representing 275,000 cubic feet per second, passes over the falls continuously. Its daily force, some 7 million horsepower, equals that of the latent power of the 200,000 tons of coal mined every 24 hours throughout the world. Think of the thousands upon thousands of stately ships furrowing the ocean, the myriads of locomotives that flash over the ironways, the huge boilers bringing movement to countless factories. Their combined average energy is not equal to that running to waste at the roaring of the waters. Now, were Niagara situated in some desolate, sterile Arctic region, the eyes of engineers would still turn longingly to its enormous power. Nature has, however, dealt kindly with the human race in placing the falls where they are. In a healthful country, teeming with natural resources, among peoples of superabundant energy, it would be almost less a matter for surprise were the waters to leap upwards than that the enterprising American and Canadian should fail to utilize the vast power flowing past his doors. Niagara Falls are the right thing in the right place. The time has come when toll can be taken of those rushing waters. Electricity, the genius of the 20th century, has long burst its swaddling bands and can be united to water in a most advantageous partnership. Ever since the first sawmill was set up at Niagara in 1725, the idea of subjecting some part of the enormous power of the falls to industrial uses has stirred the inventive faculty of engineers and manufacturers. Early in the 18th century they cast about for a means of harnessing this lavish provision of nature, but the scientific knowledge of the world had not yet sufficiently advanced. In the 19th century, steam and steam power made such progress that manufacturers quitted the riverside for the coal field. But the advantages of water were not forgotten. In 1842, we find Augustus Porter, one of the principal proprietors of Niagara, proposing a system of canals to the high bluffs overlooking the falls, whence the water might fall over large wheels to drive the machinery of mills. As a result of continuous negotiations, a syndicate of gentlemen obtained a right to construct a canal 35 feet wide, 8 feet deep, and 4,400 feet long, from the water of the upper Niagara River to those bluffs, where, by 1885, the available capacity of the canal was being converted into some 10,000 horsepower. Still greater projects were to follow. Mr. Thomas Evershed, an engineer who has done noble work in protecting the falls from utilitarian desecration, was called upon the same year, 1885, to develop a plan whereby the beauty of the falls might be preserved, and at the same time a large bulk of water turned to practical purposes. He conceived the idea of tapping the Niagara above the falls, precipitating the water into a huge pit where machinery would be stationed, and carrying the waste along through a large tunnel nearly 1.5 miles long to an outlet below the falls. His plan was strongly opposed as impracticable, but in spite of discouragement, 8 gentlemen of Niagara obtained from the New York legislature in 1886 a special charter, granting the right to take from the upper river sufficient water to develop 200,000 horsepower. A second concession, of a later date, from the Canadian government permits the same company, now known as the Niagara Falls Power Company, to draw from the Canadian side an additional 250,000 of horsepower. It has been estimated that the difference of level made at the edge of the falls by the withdrawal of all this water will be but a few inches, not enough to detract in any way from the scenic effect of Niagara. The company also bought land extending for about 2.25 miles along the river, intending to lease or sell it for factories as soon as the plant was in working order, and to erect on it a residential quarter for the operatives. On paper, the company's prospects were decidedly attractive. Their total horsepower represented more than a third of the total produced by water in the States in 1880. Niagara was within a night's journey of Boston, New York, and Philadelphia, Chicago, Pittsburgh, Toronto, and Montreal. Within a radius of 400 miles dwelt 1/5 of the population of the States. It was the natural port of the Great Lakes. It also lay in the neighborhood of the great coal fields. This last consideration raised the question: could Niagara power compete successfully with steam-made power? After careful consideration, the company decided that it certainly could, and might even be carried at a profit into the coal fields themselves. As soon as great financiers had lent their names and support to the undertaking, the officers and directors of the company proceeded to attack the problem of how best to convert the water they had permission to control into energy. The problem, says Mr. L.B. Stillwell, electrical engineer of the company, was one without precedent in its magnitude and almost without parallel in its significance. The promoters of the scheme made up their minds to spare no expense or trouble to ensure the installation of the best machinery in the best possible manner then known. They called in to their aid leading engineers and electricians of all countries, thus exhibiting a breadth of policy superior to all motives of natural prejudice. As regards the method of supplying and carrying off the power water, it was finally decided to construct a surface canal above the falls, 250 feet wide at the mouth, and running into the land for a distance of 1,500 feet to the site of the powerhouses, the latter to contain eventually machinery capable of delivering 50,000 horsepower. A wheel pit would there be dug to a depth of 178 feet, and connected at the bottom with a tunnel 7,000 feet in length, having a slope of 6 feet in 1,000, and a maximum horseshoe section of 21 feet by 18 feet 10 inches. Water would flow through the tunnel to the outlet below the falls at a rate of a little less than 20 miles an hour. The questions of machinery and power distribution were not settled so easily. In the first place, the forms of turbine most popular at that time did not appear convenient for the installation in question. In the second, given a most efficient turbine, how was the 5,000 horsepower developed by it to be brought to the surface many feet above? In the third, how was the power, when delivered to the surface, to be distributed in the neighborhood and at a distance? The company did a very wise thing. Instead of sitting down and trying to think the matter out by themselves, they appointed an international commission, consisting of Sir William Thomson, now Lord Kelvin, as chairman, Dr. Coleman Sellers of Philadelphia, Lieutenant Colonel Turretini of Geneva, Professor G. Mascart of the College of France, and Professor William Cawthorne Unwin, Dean of the Central Institute of the Guilds of the City of London. This commission, established in London, was empowered to obtain records of all sorts that should help to solve the three problems now before the directors of the company, and to award $22,000, £4,400, in prizes. Inquiries and examinations concerning the best-known existing methods of development and transmission in England, France, Switzerland, and Italy were made personally by the officers and engineers of the company, and competitive plans were received from 20 carefully selected engineers, designers, manufacturers, and users of power in England and the continent of Europe, and also in America. Footnote: Cassier's Magazine. End footnote. The first important result of this commission was that Messieurs Feisch and Picard of Geneva were selected to design the turbines. The character of a turbine is probably widely known to the public, but to prevent any possible misconception, we may here state that a turbine is composed of a number of vanes set spokewise round an axis, and enclosed in a cylinder in such a fashion that all water passing through the cylinder must push the vanes aside in its course, imparting to them and their axis a circular motion. In order to make the water more effective, fixed vanes are attached rigidly to the cylinder walls at a short distance from the moving vanes, so as to deflect the water onto the latter at the most efficient angle. The turbine principle has lately been employed largely with steam to drive torpedo destroyers and merchant vessels at high speed, and to supply motive force for dynamos and the ventilating fans of mines. The Niagara turbines are about 5 feet in diameter and have a vertical axis. A peculiarly ingenious feature of their construction is that they are made in 2 stories, as it were. The top vanes the larger, and the water from the penstocks or supply pipes is made to enter between the 2 sets. The pressure against the upper vanes being greater than that against the lower vanes, the turbine is endowed with sufficient lifting power to support the entire weight of all the revolving parts, namely the wheels, the vertical shaft, and the revolving parts of the generator driven by the wheel. The mention of the shaft brings us to the second point under investigation, the best means of bringing 5,000 horsepower from the point of development to the surface. For this purpose it was decided to employ a shaft of steel tubes 38 inches in diameter, contracting at intervals into a solid bar 11 inches in diameter, to run in journals for the sake of steadiness. At the upper end of the shaft should be placed what? The answering of this question demanded the most careful investigation. In 1890 there were people to plead for 4 different methods of power transmission. Some could point to the good work done at Schaffhausen and elsewhere by turbines driving manila and wire ropes. Others to Geneva, where turbines transmitted hydraulic pressure for considerable distances through pipes. At Paris, again, the compressed air system had been largely developed, and in America this method had a stout champion in George Westinghouse, the famous inventor of the air brake for trains. The 4th method, that of transmission by electricity, could, however, produce the best credentials, a particularly good proof of its reliability being afforded at Domaine in the Dauphiné Alps. The power for a paper mill is there drawn from a glacier in the mountain 4 miles away, where the powerhouse is inaccessible for 3 months of the year. In spite of sleet and snow and storms and intense cold, the conducting wires do their duty continuously and well, with great profit to the owner of the mill to which they supply power. As the Niagara plant was to be on an unprecedented scale, the dynamos were of unequaled capacity, able to produce currents in large quantities. These generators differed from the usual type in one very important particular, that is, that the position of the stationary and moving parts was reversed at Niagara. It is customary for the armature, a series of coils of insulated wire, to be rotated rapidly inside a circular ring called the field ring, to the inner face of which are attached a number of powerful magnets. In the Niagara installation, the armature is fixed, and the field ring made to revolve. We may assume that the armature in question resembles a huge cake with a large hole cut through the center. The turbine shaft is extended to pass through the cake and project some distance above it, ending in a taper which fits tightly into a hole in the center of a horizontal plate or driver of rather larger diameter than the armature. The field ring is bolted tightly onto the end of the driver, and the shaft, driver, and ring have together a decided resemblance to a Chinese umbrella, the turbine shaft representing the handle, the driver the top, and the ring the hanging sides. It is a noble umbrella indeed, the carrying of which would need the sinews of a small celestial army. Its weight is 79,000 pounds, or about 35 English tons. This includes the shaft, the driver, and the ring with its pole pieces and bobbins, each of which weighs more than a ton. The whole revolves at a rate of 250 revolutions a minute, giving the flywheel an effect of 1,274,000,000 pounds. One advantage of this arrangement is therefore obvious, that the need of a special flywheel, as originally designed, is done away with. Another is that the magnetic attraction between the field magnets and the armature acts against the centrifugal force, tending to burst the ring, and so increases the factor of safety of the ring. This last is worthy of a few lines to itself. Its diameter is 11 feet 7 1/8 inches, its depth about 4 feet. The ring is forged in one piece without weld from a nickel steel ingot 54 inches in diameter and more than 16 feet long, through the center of which a hole was bored preparatory to expansion on a mandrel under a 14,000-ton hydraulic press. The Bethlehem Iron Company was responsible for the forging, and the Westinghouse Electric and Manufacturing Company for the truing and turning up on their mammoth lathes. The Niagara Falls Power Company have on the American shore 2 powerhouses. Each is designed to accommodate 10 generators, giving a combined output of 50,000 horsepower. The one is finished and in full working, and the other rapidly approaches completion. Beneath the stately row of dynamos, which we see on entering a powerhouse, yawns the wheel pit, 463 feet long, 20 broad, 180 deep, a huge slot cut out of solid rock. If we are permitted to descend, we find men busy attending to the bearings, watching that the oil supply keeps down their temperature to the proper figure. Near the bottom, the turbines hum on their platforms of stout steel girders spanning the gulf, and fling vast quantities of water into the nether darkness, whence it finds a path through a side tunnel into the great main tunnel that occupied 1,000 men continuously for more than 3 years, in the removal of over 300,000 tons of rock and the placing of 16 million bricks for lining. Near the portal, the grade falls very suddenly, so as to permit the discharge of 1/2 of the flow from the tunnel below the surface of the rapids. In the powerhouse, flanking the generators, stand 2 platforms of white enameled brick, each nearly 20 yards long and some 13 feet wide, surmounted by 8 upright stands on the face of which are many indicating instruments. These structures are technically known as the switchboards, to each of which is conveyed the total 25,000 horsepower from a group of 5 generators. The switchboards are the main nerve centers of the plant, from which its various functions are directed and controlled. Upon them are located instruments and appliances, by means of which the attendant is always informed as to the output and voltage of the various generators, and which indicate instantly the nature and, within certain limits, the location of any disturbance in any part of the system. In front of the attendant are 100 levers, controlling pneumatically the great dynamo and feeder switches and auxiliary switches. Here, by the crook of a finger, the attendant can at will cut off instantly the entire supply, or any portion of it. Footnote: Mr. Philip B. Barton, in Cassier's Magazine. End footnote. In comparison with the power handled, the number of men required to control it is small, but the well-being of so many thousands depends on the small band in the powerhouse, that it becomes an absolute necessity for each man to be specifically trained, alert, resourceful, to meet any emergency that may arise. The working of the generators goes on night and day, and the employees are therefore divided into 3 shifts of 8 hours each. At the head of each shift is the electrician in charge, whose particular duty is to operate the 2 main switchboards, and his post, the captain's bridge of the plant, as it has happily been called, is switchboard number 1. An assistant electrician has charge of switchboard number 2. A shift foreman is responsible for the operation of the motive power plant, having under him oilers to tend the bearings, laborers to keep the inlet racks to the penstocks free from eelgrass, ice, and drift, and the man who looks after the elevator in the wheel pit. Other officials are in attendance to repair the machinery at any point, whether hydraulic or electrical, and attend to the telephone, through which important orders may come at any moment. The current manufactured by the generators may be used either locally or at a distance. In the former case, the pressure, or voltage, is that of the generators, but for transmission to distant places such as Tonawanda or Buffalo, 20 miles off, it would be unprofitable to use so low a pressure on account of the loss that results from the resistance of the conducting cables. The current is therefore stepped up, or increased in intensity, to 11,000 or 22,000 volts, just as water or gas is pumped at very high pressures through long pipes. On reaching the receiving end of the transmission cable, it is stepped down or reduced by transformers for local uses and converted, if necessary, from alternating to direct current. Niagara Power was first sent to Buffalo in 1896. The cables are slung on stout poles 35 to 65 feet high, placed about 60 feet apart. Porcelain insulators of unusual size are employed to protect the cables from leakage, and in order to maintain an efficient guard of the line, the Niagara Falls Power Company has purchased a strip of land 30 feet wide, reaching from the falls to Buffalo. The line is patrolled night and day by men who are able to communicate by telephone with headquarters. At the Buffalo Exposition of 1901 was witnessed the most magnificent display of electric illumination that ever gladdened the eyes of man. The central point of the display was the electric tower surmounted by a superb figure of the Goddess of Liberty. Several hundred thousands of 8-candle power lamps had been arranged along the angles and edges of the building and its chief architectural details. At a given signal, the operator in the electricity building started a small motor, controlling a worm gear that slowly poured into the lamps the whole of the power taken from a generator at Roaring Niagara, 20 miles away. The gradual change in myriads of lamps from faint luminescence to full incandescence came as a revelation of beauty to the thousands of spectators in the grounds below, and soon after a huge searchlight swept the horizon, even to the mighty cataract from which it derived its force. The purposes to which Niagara Power is already turned are legion. The population of the northwest corner of New York State has become dependent for many conveniences and comforts on the energy issuing in vast quantities from the grey limestone powerhouses flanking the sides of the Inlet Canal. 4 cities, of a combined population of 500,000, are lit throughout by Niagara Force, which also operates their 350 miles of streetcar track. In Buffalo, the Tonawandas, Lockport, and Niagara Falls, 50 large manufactories, representing a capital of $100 million, depend entirely for their success upon a constant supply of current from the company's generators. And so efficient is the organization of the company's plant that during a period of nearly 3 years, total interruption of power has occurred but once, and then only for 18 minutes, on account of an ice jam in the river. As the plant is increased, the possibility of interruption will become even slighter, since the switchboards are so arranged that the current from any one group of generators can be switched in a moment into any supply line. The rapidity with which improvements in electrical apparatus succeed one another may be gauged from the fact that, in the second powerhouse on the American side, the 5 turbines last put in will be of a fixed field ring type, an improved reversion to old practice, while on the Canadian side, where tunnel, wheel pit, and intake canal for a capacity of 100,000 horsepower are being completed, the company is establishing dynamos producing the enormous figure of 10,000 horsepower each. This increase in the size of the unit is, of course, the result of proved economy in larger generators, as regards cost per horsepower in the construction of the generator, and the turbine to drive it, and the space required in the wheel pit and powerhouse. It is possible that in the future we shall see far larger generators even than these in common use, for the big thing of today becomes the normal practice of tomorrow. We should at least mention, though full details of management, construction, etc. are not at the author's disposal, an independent company, known as the Niagara Falls Hydraulic Power and Manufacturing Company, which already develops and sells 35,000 horsepower to various industries. This company's powerhouse is situated below the falls. It draws its supplies from a canal that connects the upper river with the edge of the bluffs, whence 3 penstocks, 11 feet in diameter, conduct the water 210 feet vertically to 14 turbine wheels of from 2,000 to 2,500 horsepower each, connected directly to generators coupled at each end. From these generators, the current is led to the top of the bank by means of wires and aluminum bars built along the side of the penstocks, and thence in underground subways to various consumers. With power so abundant, it may well be cheap. In how many regions of the world could you, for the sum of $8, £1 12 shillings, obtain from year's end to year's end without a break energy representing 1 horsepower? Having these figures before us, we can understand why the Pittsburgh Reduction Company, which controls the aluminum industry of America, left Pittsburgh, where good coal cost but 68 cents, 2 shillings and 10 pence a ton, and migrated to Niagara, and how it comes about that many manufacturers can here save enough on power in 1 year to pay for building and cost of removal. The company just named produces pure aluminum, a metal distinguished by its lightness, beauty, and freedom from corrosion, from an oxide of alumina, by smelting the latter in carbon-lined retorts, which act as one terminal of a heavy electric circuit, massive carbon rods suspended above the crucibles forming the other pole. The carborundum company also employs intense heat. Electric furnaces of today are used at a temperature of 7,000 degrees to smelt carborundum from its ore into crystals, which are ground into powder and pressed into various forms for grinding purposes as emery, large wheels for shaping tools, or tiny discs for smoothing teeth. Among electrolytic and electrochemical processes, none are of greater interest than the carborundum processes, whereby an artificial abrasive is made in much the same way as that which brought the diamond into existence. Great factories are springing up for the manufacture of carbide and calcium, and other chemicals. Thomas Edison, the great electrician, has prophesied that Niagara will be the great electrochemical center of the world. It may already claim that distinction, so powerful an ally is an unlimited supply of cheap power to the chemist. Paper, silver plate, graphite, lamp, cloth, and steel factories are rapidly rising within sound of the falls. Electricity heats the ovens in the huge establishments of the Natural Food Company. At Tonawanda, electricity saws and planes vast stacks of timber. At Lockport, it whirls heavy trains. At Buffalo, it runs the streetcars, prints one of the leading newspapers, handles thousands of tons of cereal, helps in the creation of steel bridges, operates refrigerators, supplies the motive power for great dockyards, tan yards, breweries, and pumps. At Niagara, as a result of this newborn power, a great city is springing up with mushroom speed, a city free from smoke, gas, ashes, an ideally clean city. 5 trunk railways lead westward from it, 5 to New York, 5 to Boston. On the completion of its docks, Niagara will be the eastern terminus of the Great Lakes Basin, at the greatest transshipment point of raw material in America. All things augur for Niagara a future comparable to the present of Chicago. It is a matter for thankfulness that the great power installations have been so arranged as to leave the picturesque beauties of the falls unharmed. Tourists will still find the huge cataract a thing to gaze upon with rapt admiration, despite the turbines pulsing with mighty energy not far away. The public-spirited action of the company is further seen in the industrial village of Ecota, which they have built for the employees in the factories. A few years ago, the 84 acres on which it stands was waterlogged meadowland, subject to inundation by the streams that run on 2 sides of it a few feet below its level. The company therefore built a high dike all round it, and, as it was impossible to raise the area to a height at which it would drain readily into the river, they instituted a system of deep drainage, which, traversing the city in all directions, discharges into large pits, whence the water is pumped into the streams. So carefully has this been done, that rains no longer make the earth heavy and muddy, nor does the sun scorch it into cracked clay and dust. Lawns and trees flourish, and wet cellars are unknown. broad roads intersect the property on a systematic plan, passing between rows of trim houses well provided with modern comforts, running water, electric light, and a wholesome sanitary system. The streets are lit with large clusters of lamps by night. Boughs of trees give grateful shadow by day. A frequent service of electric cars runs at all hours. And last but not least, rentals are as low as $9 a month, light and water included. The village of Ekota has been evolved, writes Mr. John Bogart, footnote, in Cassier's Magazine, end footnote, in accordance with the careful study of the men to whom was committed the responsibility of the solution of a complex problem. A district not fit for comfortable residence has been transformed into an ideal healthful village. Ground upon which no vegetation would thrive has been changed to a region of velvet lawns and blooming gardens. Roads which were a discomfort from dust or annoyance from mud have been made into well-paved, beautiful streets. An attractive expanse of poor meadowland has become a model town. We may here say farewell to the great Niagara Falls, and in conclusion turn our thoughts for a moment to the Zambezi, where the Victoria Falls, twice as broad as those of Niagara, have a sheer drop of nearly 400 feet. Today, in California, power is successfully transmitted for nearly 150 miles, and with this precedent it is to be hoped and expected that in the future water power available in unequaled volumes at the Smoke That Thunders will be utilized to aid the development of the great mineral resources of Rhodesia and South Central Africa, converting what is now semi-explored territory into centers of industry. Note: on the Canadian shore, there are at present in progress two separate undertakings independent of the Niagara Falls Power Company. That is, the Ontario Power Company, which is now constructing a proposed initial development of 30,000 to 50,000 horsepower, and the Toronto Niagara Power Company, which has recently commenced the construction of a 50,000 horsepower plant. End of Chapter 1.